Good morning. So we'll have a rather short lecture today. I need to leave at 10 o'clock, so we'll have 1.5 hours. So I'll give a 10-minute break around probably, say, 9:15, and then we'll be finishing at 10 o'clock. We'll continue with this topic next Monday and next Tuesday when we resume our class at the same time, as always. So today what I'm gonna do is I'm gonna talk about the rendering a little bit more. Last time 2 weeks ago, we talked about rendering in some detail, but we covered one part of rendering. So there are two ways that we can actually do rendering. Rasterization and raycasting. We did rasterization. We talk about rasterization in the context of a graphics pipeline and using a graphics card, a GPU. Today I'm gonna go back to that again, but this time talk about raycasting instead. And I'll tell you about a little bit basics of raycasting and how it works so that you have an idea the difference between these two techniques. So raycasting is a rendering technique, and what you do is you take you essentially take your scene, and the scene is represented probably as faces or as some geometric objects, maybe a set of triangles, oriented triangles, or just maybe, let's say, some primitive geometric shapes and a combination of those with a camera, and you render those that scene into your, let's say, camera's image plane. And this can be again done through either rasterization, as we discussed the other time 2 weeks ago, or you can also do raycasting, and again we are going to talk about raycasting today. So the idea of raycasting is going to be very simple. What we are going to say is, okay, our object, let's say our object, and each pixel in our, let's say, image plane is going to be actually corresponding to a ray, and this from viewing point to this ray will actually somehow, this has to actually, if it is visible to us, and if there is a pixel here corresponding to the image itself, this ray then that we form from image center to the pixel here, the extended ray should hit the object, because if we invert this, in reality there has to be a light from here and coming back to us. So this is the kind of the idea where raycasting actually says, okay, I will take my ray of this ray and I will actually cast this into the scene and find which point in the scene actually corresponds to or will contribute to this pixel here. Okay, and this way you can do the basic of, let's say, rendering. This was similar. I mean, the idea was similar with rasterization, where we would take, let's say, a triangle in the scene, some basic shape in the scene, and find out if that triangle or that basic shape is actually seen by the camera. And then once we see that, we project the locations of those into the view as let's say a triangle, and then fill in the gaps of that triangle or whatever shape that we were talking about in using some rasterization. All right. So this time what we are going to do is we are going to actually do this per pixel, and each pixel will be actually found through raycasting. Of course, there are going to be, let's say, differences between these two techniques, and raycasting in principle can actually generate, let's say, more detailed images, as we are going to see, but it could be quite expensive as well. So rendering a scene through raycasting might be actually an expensive proposition, expensive method. However, in the context of augmented reality, this could be actually an interesting approach as well, because in the case of augmented reality, we are going to actually, we know that we are not going to render the entire scene, right, or entire image. Only the parts where the object of interest is actually in this case, the object of interest is our virtual object, where the virtual object is visible, and we are not going to actually render the rest of the scene. We don't need to render the rest of the scene. Therefore, it might be interesting to look at actual raycasting from that perspective, that since we are going to be only rendering on a certain part of the scene, the process could be actually, let's say, efficient enough for raycast for rendering in augmented reality. Of course, this will depend on the hardware that we use. So if the hardware, let's say, we has certain, let's say, GPUs and so forth, and they are, as we have seen, they are quite efficient, designed for they are efficient and designed for rasterization, then it may not be actually as efficient as that, but we can also use it in different ways. For example, what we can do is we can say, okay, if I want to know where this pixel is in the scene and which object actually it belongs to, I can do this raycasting and actually find out which object is actually that it belongs to. Or if I, let's say, I can use other things, like if this is a head-mounted set, and if I have my finger here, for example, in the middle, somewhere here, in the middle of the scene, let's say between me and the scene itself, I can actually trace, let's say, if I'm able to trace the location of my, let's say, hand, and I can actually use that hand to actually select objects, especially virtual objects in my scene, right? Or real object as well, if I have the models of real objects. So if this is a real object and my hand is somewhere here, I can actually do this ray tracing again the same way, and trace the ray and see where it actually hits in the scene, be the actual object or a virtual object. Of course, actual object needs to be a kind of one-to-one map to a model, so that I can know where that model is. So this is where the raycasting can be actually useful. What's happening here? Something is happening. All right, anyway. So it could be useful, the raycasting could be useful to actually find out where certain objects or select certain objects in the scene. So again, we want to actually do this rendering and we want to see how this rendering can be done, can be achieved using raycasting. So then the question is going to be, once we actually have this ray hitting this object, we are going to decide what color do we want to actually put for each pixel, right? So this is the color is going to come from here. Now, perhaps what we need to also do is we'll need to also see if I have a light in the scene, and I want to see actually what the lighting is going to be as well. So there are several things that we need to decide for using to use the raycasting. We have to actually do some decision on the color, and also it will again be depending on the which surface it hits, where the light comes to that surface, of course, and then if there is any sort of shading or anything that goes on the surface itself. So as we have seen, rendering was referring to the entire process that produces a color value for pixels given the 3D representation of our scene. Again, in the context of augmented reality, we have two parts of the scene that we are interested in. One part we actually use for generating a virtual objects image. So these are the virtual parts of the scene that we are augmenting the scene. And also other parts that actually corresponds to the reality, and we want to actually use that perhaps to track where the reality is and so forth. We may or may not render that every part of the digital in the scene. So we may only render a certain part of the scene. So if we actually treat pixels as convert pixels as to rays and figure out visible point that actually contributes to that pixel, or let's say visible by that pixel, then we actually can generate this rendering. And this process is sometimes called hidden surface problem or visibility problem. And we can, of course, there is the question of how many rays per pixel we have to actually use. We can use one ray per pixel, but if you see it here, for example, if I have just the center of the pixel here as my, let's say, ray, it may actually correspond to your pixel may correspond to a large portion of the scene. So it may not be just a single point that it's actually kind of getting lights from. So it might be getting lights from many points. Of course, if point is a, let's say, a dimensionless thing, it will be infinitely many. But the question is, if I have, let's say, if I look at the corner of the pixel here, and if that corner, let's say, points to the nose, and then the other corner points to the, let's say, to the mouth, then we have a problem here that actually this pixel sees, in general, a large portion of the object. And the question is, how are we going to actually get that? So that can be resolved perhaps by, let's say, casting multiple rays per pixel, for example, instead of just sending the center ray. We can also look at the corners, or we can actually do a finer grid per pixel. We are not gonna bother with that for the time being. We are gonna assume that we have only a single ray per pixel, and we'll actually see how that is working. Okay, so to do this, we have seen that there are two possibilities. One is raycasting, the other is rasterization, and we'll have a pinhole camera, or we may have actually other cameras as well, but we'll assume that for the time being we have the pinhole camera. And rasterization, we have seen rasterization before. Now we are going to talk about first just a simple camera and ray generation, and for starting with raycasting basics, we'll go to camera and ray generation, we'll do ray plane intersection, and then we'll also see how it is done with ray sphere intersection and so forth. So raycasting algorithm is a very, very simple one. It goes as follows. You have, for every pixel in your scene, in your image, you construct a ray from the eye. So eye is here. This is the center of the imaging. So this is the 0, 0 for our camera, right? So you have a pixel here, and then you construct a ray that is coming out of from the center of the camera, going through the pixel. Let's say this is the center of the pixel for the time being. This is assuming that your pixels are some sort of rectangular shape. You can choose a center to be the actually where that ray is actually going through. Now we have this ray. So we construct the ray from the eye, and then for every object in the scene, we do this one. We find the intersection with the ray. We look at the scene. We say, okay, in this case, we have 5 objects in the scene, and we look each object and say, okay, do you intersect this, or does this ray intersect that object? Yes, no, 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 yes, right? So we have all these. And then what we do is we get the closest object to the eye as our contributing pixel. All right, so in this case, you see that this ray intersects first object, this first sphere here, and the second sphere here. And therefore, I know that actually in this case, I have the sphere. This one is actually is where I want to get my color value or whatever. This pixel is going to be seeing this object, not this object here. So just keep the closest one as the intersection point, and then use that to actually shade later on. So then what you do is, once you decide that this is the surface that we are going to actually be seeing through this for this pixel here, we just shade it. Shading will actually look into certain lighting and certain surface properties of the object. You can see that this algorithm is a little bit different than the rasterization algorithm that we had. In the rasterization algorithm, we were actually starting from this way here. For every surface or primitive in the scene, we were actually projecting those primitives into the image plane, right? It was going the other way around. And then we were actually doing some sort of, let's say, depth analysis and so forth. Now, the major difference that you can see here is going to be, if I have, let's say, if I have algorithms that can work very well with, let's say, if I have, let's say, very few, let's look at this case, right? So this simple. If I treat this scene as, let's say, as the primitives that rendering rasterization requires, like triangles, I can have many triangles for this sphere, many triangles for this sphere, and so forth. So depending on level of detail that I want to achieve, perhaps I will have 100,000 triangles per sphere here. So you can get when the complicated objects like this, or let's say when the basic shapes of like this, these basic shapes can create a lot of surface and elements like triangles. And the rendering algorithm that we have seen will be actually processing all those triangles. There are techniques to remove them and so forth, but there still you have your algorithm is proportional to the number of triangles in the scene. Here though, it's gonna be proportional to the number of objects in the scene. So if your objects in the scene are triangles, then this will be quite expensive as well. So you'll need to actually take this ray, do the intersection for each object, let's say 1,000,000 triangle in the scene, and then once you find that triangle closest to you, then you'll actually know which triangle to render, and then you can go to the shading part of the thing afterwards. Whereas that other pipeline that we have seen would actually do this probably very similar, but the other way around. There is no ray casting anymore. It's just just a projection. And if you have a simple, let's say, GPU with simple arithmetic operations, namely just some matrix multiplication by and division, you can actually achieve this quite efficiently. However, if your scene is actually composed of, let's say, some other geometric objects where it is easy to do intersection, find the intersection with your ray, like let's say a sphere, then this could be actually quite fast as well. So instead of now dealing with millions of triangles in this case, you would be dealing with only, let's say, 4 spheres and 6 faces of your cube here. So it may be actually advantageous if you have fast algorithms to actually find the ray intersection with your objects, and if your objects are, let's say, simple objects in terms of actually or compact objects or simple objects, whatever, that intersection actually works very fast. In that case, this could be quite fast as well. Of course, the shading is going to be involving the surface properties, the surface normal, direction to the light, the viewpoint, and the material properties as well, diffuse or specular, and so forth, and the properties of the light, where the light is, what the intensity is, and so forth. Of course, shading will, let's say, shadow will be an important part, and so forth. So this is shading is an important part, as we have seen before. We are not going to worry about this as much here. We are going to talk about more about the tracing part, the ray tracing part, or ray casting part of the thing. So as I was trying to say, there is also something called ray tracing. So ray casting is actually the simplest difference between these two is ray tracing. You actually trace your ray not just from your eye to your object, but also you worry about actually, let's say, other things like this, how this thing is actually seeing the other part of the lights, and so forth. So you cast a ray here, then you know where your thing is. But to look at the secondary, ternary effects of light hitting here, you can use ray tracing. So you can say, okay, yes, I actually see this point from my camera, but is this point is visible from my light. So in that case, ray tracing actually is in a way going from the light to the object and to the camera. So whereas raycasting is only interested in finding out if that object is actually, which object is visible. So these secondary rays, raycasting is actually doing the eye rays only. Tracing also looks at the secondary rays and so forth. And you can see that finding the secondary rays are going to be much more complicated, and it will involve a lot of calculations. Therefore, it will be computationally very complex. So for the time being, we'll be actually dealing with ray casting only, but ray tracing will actually help us do a lot of other fancy stuff with rendering, like finding indirect illumination, finding reflections, finding refractions, finding what is called caustics, and finding shadows. You see here, for example, there is a shadow of this object, and this object's shadow which actually is coming from here. Here you see that there is actually a shadow, but also there are refractions and caustic effects and so forth. So this is very, and you see also something here. These are very, let's say, realistic things that you might actually have as far as the physics of light is concerned, and you can actually use secondary rays or ray tracing techniques to generate this. Now the question, of course, is, would this be necessary for us in the context of augmented reality? Sometimes it might be, or maybe virtual reality, for example, especially in virtual reality, this could be quite important if you are looking at an object like this, and you know that this object is actually doing a lot of tricks on the light, like let's say a marble ball, then you might want to actually get all these into your raycasting system. But of course, it's going to be quite expensive, and many of these systems, raycasting systems, are not real-time systems. They are offline systems, and they are used primarily for let's say visual effects the generation, like let's say movies and such. All right, so the second part of we are going to go back to this thing again, but in detail, how we construct a ray mathematically. But the second part of the raycasting algorithm is going to be finding the intersection with the ray. So how do we find the intersection of the finding the intersection point of a normal in the scene with respect to so we want to actually, we can actually look at this intersection within a simple way. So let's start with the ray, forming the ray. So we have a ray is actually starting from your origin. So this is probably your 0, 0, 0 point, right? And we are assuming that your scene is actually transformed. It went through the model transformation already, so it's in the right place. It's in the camera coordinate system. And you have the direction. You need only the direction. And then any point in the scene on this ray is going to be simply represented as origin plus some t, some parameters. You can think of this as a distance from your eye to your center to this point, and the direction itself. So you need the origin, which is going to be in 3D, is going to be x, y, z, right? So 3 degrees of freedom. And then you need a direction. This is 2 degrees of freedom. And then you'll have this t parameter. So the ray is going to be parameterized by a single parameter, given the direction and origin is known. So array is actually parameterized only with a single parameter, just t. T is the distance between your origin and your point of interest on that array. Now, this type of representation is also good because we are gonna do ray casting, right? So one object might hit this ray from here, and then another object might hit the ray from here. Now what we can do is we can parameterize the hit points for each object with t, just a single number. And then what we are interested in the closest of these numbers or the smallest of these numbers. The smaller number, the smallest number will give us the visible point, because if the ray is actually hitting multiple objects, the object that actually gives us the smallest t is the one that actually is visible. The rest will be actually behind that first object. So this is we are gonna be looking for t larger than 0, but the smallest of that number. So smallest positive number is gonna be our answer. So this is good. Actually, this raycasting machine has been actually used in the past. This is one of the guys that actually used this in the 16th century by actually looking at these type of things. So Albrecht Dürer actually had this one. So what he would do is he would actually put an object here, and then he would actually put this thing here, put a, let's say, from the perspective of this thing, puts a point here, and then we'll close this one, and then that will actually give you a point here, right? And then you can do this repeatedly, and then you can actually trace your object this way. So this was a kind of an interesting thing. All right. So how do we construct an array? Let's go back to that one. So the way that we actually do this one is we start with the camera description, of course, and for the camera we use our pinhole model. So the pinhole model is a simple model, and we have the eye center, and we have the kind of the viewing frustum, right? And what we have is we have our ray here is actually is just the center is known 0, 0, so we don't need to worry about the center in that case. And then our ray is gonna be whatever in that image, wherever that pixel is, just 2 degrees of freedom, right? So we also have these the camera coordinates u, v, w, of course, the horizontal u and vertical v, and direction w. All right. And the frustum actually gives us the limitation of the image plane. So image plane is not infinite, therefore we'll be only seeing a portion of the scene at a given time. Of course, we have this aspect ratio and so forth, but we are not going to be interested in that for the time being. What we are going to do is we are going to assume that the image coordinates are normalized, meaning we'll be actually normalizing everything from -1 to 1 for the x direction, and for the y direction we'll be actually normalizing it from, again, -1 to 1. So we can do this one, there is no issue. This is the normalization, if you recall, in our calibration steps, this was the normalized camera calibration, was camera coordinates. So how do we generate the ray in 2D? Let's look at that one. So this is the center point we have, and this is the point that we are interested in. And I want to actually find out this ray. And this is a field of view of my camera, and this is just the x direction, and x direction is limited from -1 to 1. All right. So in this case, I can actually do this one very simply. The way that I can look at actually, let's say, this d distance is my, if this is the field of view corresponding to my frustum in this direction. So the half of that field of view is this one. And from simple trigonometry, I can tell you that actually this d is just simply 1 over tangent alpha over 2, right? So this is very simple. And then this point here, this point is the ray. P, the ray is going to be P minus this one. So this minus this will give me this ray, right? And the way that I can actually now represent this one is the x location of the point in the view here. So this is the x direction, right? Times u, and then this is the d times w, right? So now I have my representation already. In that case, PT is, I can get the PT as E plus TD. So E is 0, 0 in usually, but anyway, and TD is, D is this direction, and D is actually just simply this R, this direction ray is actually normalized. Very simple. And this normalization, if you look at this one in 3D, R is now X times U, Y times V, including the aspect. Assuming the aspect ratio is 1, then it is just Y times V and D times W. And these are the base vectors, of course. And if the camera is, let's say, is identity, meaning I actually, my coordinate, world coordinate system is a camera coordinate system, then U is going to be 1, 0, 0. This will be 0, 1, 0, and this will be 0, 0, 1 anyway, right? In that case, this will be very simple. And aspect ratio, again, you may or may not have it, but if you have non-square viewports or viewing frustums, then you can actually have these type of things that say 16 by 9. This is like a widescreen TV. Okay. Now, once we have the ray, now we know how to represent a ray. And what we want to do is we want to actually find the intersection of the ray with our objects. Okay, let's start with a plane. Assume that our object is a plane, and I want to actually find the intersection of that object with my ray. So my ray is just a simple R0, the starting point, plus T times RD, the direction of the ray. And the distance to T, this point from the origin of the ray is gonna be T, right? This is how we represented it. This is called explicit representation. All right. Now, if I have a plane, an infinite plane for the time being, we don't care about actually. Let's start with assume that we have an infinite plane. We can constrain that plane with its boundary, but for the time being, assume that it is a infinite plane. A plane is can be represented by two things: a point where the plane passes through. That's gonna fix the plane's let's say placement in the space, but it won't fix the orientation. So there is this orientation, and the orientation is gonna be actually fixed by the normal of that plane. So if the normal is ABC, and the orientation is the plane on the point on the plane is x0, y0, z0, then we can actually have an implicit plane equation by ax plus by plus cz plus d equals 0. D is the kind of the distance of that plane from the origin of your coordinate system, world coordinate system, wherever that is. And you can also represent it by just n times p. This is where the point is, plus d. Now, if the point is on the plane, if the given point is on the plane, then you'll have a 0 here. If the point is not on the plane, you'll have either a positive number, which is on the positive side of the plane, like here, or it's gonna be on the other side of the plane, like here. All right. So this is now a good idea. Now what I have is I want to see if a given point is on the plane, right? And my point was PT. This point was. I want to see if this point is on the plane. Now what I can do is I can simply say, okay, if my ray intersect this plane, then it must, this PT, when I put PT here, n times PT plus d has to be 0. If this is the case, then it should actually hit this plane, right? Then I can actually find the intersection point of that thing here with t. So I know n, I know d, and p is actually just parameterized with one parameter, and I have one equation with one unknown. It's just a simple thing to solve for this one, and then now I know that this thing is gonna be hitting the plane, right? So at that, and any plane with a, let's say, any infinite plane will intersect my ray anyway, unless my ray and my plane is kind of, let's say, parallel to each other. Then I may not be able to actually find that thing, which would probably say that you're not gonna be able to find any t, or t is gonna be on the minus side of the thing, and so forth. I can actually do this one. So I put this guy on this, and I find the solution. I found the solution for t. So this says actually that this is just an equation, and if I find a t, then I find actually the intersection of that plane with my object, or if I know the point itself, then I can only do a check if that point is actually on that plane or not. So if I actually place this on my plane here equation and say, okay, this point should be on the plane, then I have this equation, and then t is simply d plus nr0 divided by n times rd. Okay, so you can see that for a given plane, I have this nr0 fixed, right? So if I have multiple rays, R0 is gonna be fixed. So this part of the thing is always fixed for a given plane, right? This part is dependent on the plane as well as dependent on the direction of the your ray, the ray that you cast. All right. So now this gives us the intersection point with this. Of course, as I said, if when n times rd is 0, when this is 0, this means that actually my direction and my normal is parallel. So if a plane is parallel to my ray, I cannot find any intersection. So this will be undefined in that case. So yeah, you have to keep you have to be careful with that case. The division by 0 should be avoided there. But it's an indication that it's not going to work anyway. So you can check n times rd first and say, okay, if this is very, very close to 0, then I'm assuming that my plane is actually parallel to my object, therefore it's not my ray, therefore it's not going to intersect that at all. So then what I do is we can do now, if I have multiple planes, I can actually do a simple checking of T. I can start with the first T, and I can, when I add another T, I can say, okay, if this T is smaller than my current T, then I will take that T as my current. And then also I need to make sure that this is within the viewing frustum that we are actually interested in. So if it is farther away from my starting point, I will not take that in. And therefore I can actually do these two checks to limit the T, and then we are done. Now this surface normal is also used in shading as well, right? So depending on the surface normal and the light direction, we can actually, we'll use this surface normal later on for shading. But the nice thing about this surface normal is, again, it is constant over the plane. So this will be giving us, as I said here, this part of the thing is going to be for everything. It will be actually for a given normal for each ray. This will be actually fixed. So I will be only worried about this part of the ray to be changing. So ray plane intersection is simple, but as we said, we haven't actually looked at if this ray is within the planar surface itself. We checked it with a plane. Let's do that with with a sphere as well. So let's see if a ray, how does the ray intersect a sphere? So a sphere is actually represented by simply an equation where we have the distance between, let's say, the point on the sphere should be, each point on the sphere should be at equal distance to the center of the sphere. So this is the center of the sphere, or this is actually the radius of the sphere. So we have P times P. This is P dot product P minus R squared equals 0. I can place my now PT as R0 plus T RD. And when I actually write this equation, I have this equation now. And here only T is unknown. And T is, this whole thing is actually an equation in quadratic equation. Now, I know that this might have no solution, like an imaginary solution, when in some conditions, and then it might have two real solutions. And in some cases, the solution might be actually the same. Those two solutions might be the same. This is gonna be when the ray actually intersect the sphere at one point here, just a tangent point. Or if it's actually piercing through the thing, then you will have two solutions, one closer than the other one. And if it is actually not intersecting it at all, then you'll have no solution. So this is now a very simple quadratic solver. You need a quadratic solver. A quadratic equation solution will give you what you need. So you do a simple discriminant analysis, and if your discriminant is actually is a real number, then you have your solutions. If it is not, then you don't have any solutions. So in that case, you are only worried about some sort of b squared minus 4ac, and then let's look at what these numbers are. In the case of actually, since RD is 1, A is gonna be 1, and B is gonna be 2DRD, 2RD is R0, and C is gonna be R0 times R0 minus R square. Okay, and you can see that R0 is actually the, if you recall, is the rays origin, and RD is the rays direction, right? And B has nothing to do with the sphere itself. Okay, and A is 1, and C is essentially just R0 square minus R0 square minus R square. So depending on the sign of B square minus 4AC, we have 3 cases. Again, one case is when this is 0, which is, let's say, the tangent, your ray is tangent to your sphere. And when this is positive, you have 2 solutions. When this is negative, you have no solution. So it doesn't intersect your sphere. So you can see that actually this is not a kind of a surprise that this is so easy to actually do this with spheres, that most of the ray tracing algorithms will show you the results with spheres because, again, this is the advantage of something like that, that you actually can just find the intersection of a sphere with your ray with just as a solution to this thing. So you just actually check this number. This is a square, just two multiplications and an addition, or 3 multiplications and an addition, and then just a check of this sign, and then you have an additional division and so forth. So this is very, very advantageous. If you were to, let's say, represent this as, let's say, as triangles, you'll have perhaps millions and millions of triangles to represent your spheres. And for shading now, you will need a sphere normal, right? So once you know that your, let's say, this is your closest point, you need a normal. And the normal is gonna be actually from the direction of the sphere to the point that you actually intersect, and then that intersection point is PT. So from sphere center to this PT will give you the normal. So this will be easy to calculate as well. And you see an example here. This is actually a very nice example, you see. And again, everything is kind of in spheres. This is some sort of fractal. And these spheres are actually are easy to manipulate. If you were to actually do this with a, let's say, with a rasterization, it could be quite involved. All right, so let's take a break and we'll continue in 10 minutes.